Uncovering the inner workings of Claude 3.5 Haiku through circuit tracing. This paper explores how a language model called Claude 3.5 Haiku thinks and makes decisions. The authors compare the model's inner workings to biology, where simple rules give rise to complex behavior. Because these models are used in important tasks, it's essential to understand how they work inside. The team uses new tools to peek inside the model and find the basic building blocks of its reasoning, aiming to better understand and improve it. The researchers build a simpler, more understandable version of the model by swapping out its complex parts for features that represent clear ideas. They use these features to map out the steps the model takes when answering questions. This map, called an attribution graph, helps them figure out what the model is doing at each stage. They also test their ideas by changing parts of the model to see how its answers change, which helps them confirm their findings. To see if the model thinks step by step, the researchers test a question that requires multiple facts to answer correctly, like figuring out the capital of the state that contains a certain city. The model seems to first find the state, then find its capital, instead of just memorizing the answer. By watching the model's internal steps and modifying them, the researchers confirm that it's genuinely reasoning in stages. When writing poems, the model doesn't just make up lines on the fly. Instead, it often picks a rhyming word ahead of time and then writes the line to end with that word. It keeps a few possible endings in mind and structures the sentence to make them fit. The researchers show this by changing the planned word and seeing the model adjust the entire line to rhyme properly with the new word. The model can handle the same task in different languages by using a mix of shared and language-specific tools inside its brain. When asked a question like what is the opposite of small? In English, French, or Chinese, the model uses mostly the same reasoning steps. The team tests this by changing the meaning of the question or switching languages midway, showing the model's logic is flexible and often not tied to just one language. Although not fully visible in the excerpt, this part likely looks at how the model adds numbers together. The goal is to see if it has a consistent way of doing math internally or if it just memorizes answers. Researchers probably find that even basic math involves complex reasoning structures inside the model. These case studies explore different situations the model might face. It can suggest medical conditions from symptoms, decide whether something is real or made up, refuse harmful requests, be tricked into breaking rules, explain its reasoning, or even pursue secret goals. In each case, the researchers uncover specific parts of the model that handle these tasks and test whether its behavior matches what's happening inside. Across many examples, the researchers notice repeated patterns in how the model works. These patterns show that the model uses abstract strategies that apply in many situations, such as planning, reasoning, and self-checking. Some of the same thinking parts show up again and again, even in very different tasks. The tools used in the study are powerful but imperfect. They only reveal part of what's going on in the model, and sometimes the explanations are oversimplified. The examples are chosen to show what the tools can do, but they may not represent every situation. The researchers are honest about these limits and hope that recognizing them will help improve future research. The study shows that looking closely at specific examples is a valuable way to understand AI models. Even though the field of model interpretability is still young, using bottom-up tools, like building simple explanations from observed behavior, has already led to useful discoveries. The researchers believe this kind of careful investigation is necessary for making AI systems more trustworthy and understandable.